Hello, welcome to lecture 16 of Elec Eng2CI5. In this lecture, I will be covering source transformations and maximum power transfer. I will show you that a voltage source in series with a resistance is equivalent to a current source in parallel with the resistance, and also will put the condition for maximum power transfer to a load. This condition is very useful and we use it very often in electrical engineering to maximize the power being delivered to a certain load. Okay, so we'll start by first by the source transformation part, and then we'll move to the maximum power transfer. In the previous two lectures, we discussed the Thevenin and Norton equivalent circuits, and we have shown that if you have a linear circuit like this one, linear network, it consists of any resistors, actually including linear capacitors, linear inductors. We'll learn about this later. But for now, we talk only about resistors. If you have any combination of resistors, independent voltage sources, independent current sources, dependent sources, these are all linear components. Then this circuit, looking into it between any two terminals, can be replaced by Thevenin voltage in series with Thevenin resistance, V Thevenin R Thevenin, or it can be replaced by a Norton equivalent, which is a Norton current embedded with a Norton resistance. So this means that these two must be equivalent, because these two are the same representation of a circuit. And we did do in the previous lectures, we did show an expression for that. For example, the open circuit voltage here is V Thevenin, while the open circuit voltage here is I Norton R Norton. So this means that if I know I Norton and R Norton, I know it's V Thevenin. Okay, the input resistance seen from this side, if you remove all the independent sources, R Norton here, and in this side, this would be R Thevenin. So remember, when you calculate the input resistance, we remove all the independent sources in our original linear circuit. So this results this Norton current to be open circuit, results in this one becoming open circuit, and results in this one becoming short circuit. So looking from this side, you see R Thevenin. Looking from this side, you see R Norton. So this means that R Thevenin is equal to R Norton, and that, as we agreed, V Thevenin is equal to I Norton R Norton, or that I Norton is V Thevenin over R Thevenin. So if you know the Norton equivalent, you know the Thevenin equivalent. If you know the Thevenin equivalent, you know the Norton equivalent. R Thevenin is equal to R Norton. V Thevenin is equal to I Norton R Norton, and I Norton is equal to V Thevenin over R Thevenin. So this is how we got this, what we got using Thevenin equivalent and Norton equivalent. But we can generalize this conclusion to say that if you have any voltage source in series with the resistance, then you can replace it by a current source in parallel with the resistance, and nothing is going to change in the rest of the circuit, for the rest of the circuit. Okay, this can be used to simplify circuits a lot. They can make the analysis much simpler in some applications. For example, if you are doing nodal analysis, you can try to convert the voltage sources that you have into current sources, because nodal analysis is easier to do when you have all current sources. If you are doing loop analysis, you have some current sources, you can convert them to voltage sources, equivalent voltage sources, and so on. Because you can really make lots of simplifications in your circuit analysis. Okay, so I decided to draw this figure to show you that indeed, from the point of view of a load, if you have a load here RL and RL, and this one is connected to a Norton type circuit, a current source embedded with a resistance, and this one is connected with a Thevenin type circuit, a voltage source in series with the resistance. What I want to show you here, that these two situations will be identical if certain conditions applies to I naught, R naught, Vs, and Rs. Okay, so from the point of view of the load, of the resistance R load, nothing will change if it has the same voltage across it and the same current going through it. Okay, so this is the main thing, the same voltage, which means the same current. So let's try to calculate the current flowing in RL in each one of these two cases. Here you have a current source I naught. This becomes a current divider. Then the current going through the load resistance is I naught R naught over R naught plus RL. This is the expression for the current divider. And the current flowing in the RL in the second circuit is Vs over the equivalent resistance, which is Rs plus RL. Take a look at these two currents. If I want these two currents to be equivalent, I can make Rs equal to R naught and Vs equal to I naught R naught. And this is what we said earlier. V Thevenin is equal to I Norton R Norton, and R Thevenin is equal to R Norton. Okay, now let's try to get the same derivation from the voltage side, from the voltage point of view. If these two circuits are exactly the same, then the voltage across the resistance RL should be the same. This is the load, correct? So what is the voltage across it? This is current I naught, and this I naught passes through the parallel combination of R naught and RL. So the voltage here between here and here, which we call here the I can call it the load voltage. So this one is positive, negative. Here we can do it this way. Okay, so this voltage is equal to what? Equal to I naught, this current, multiplying this parallel combination R naught RL over R naught plus RL. This is what we have here. So this is the voltage across the resistance RL in this first circuit. In the second circuit, we have a voltage divider. Then the voltage between here and here, the voltage across RL is Vs multiplying RL over RL plus Rs. Now, if these two voltages to be the same, take a look. Rs must be equal to R naught, and Vs must be equal to I naught R naught. Okay, and this gives us the equivalence between a voltage source in series with the resistance and a current source in parallel with the resistance. So in some circuits, if you see a voltage source in series with the resistance, if you see that converting this one to a current source in parallel with the resistance would simplify your circuit, you go ahead and do that. Remember, the parallel resistance is equal to the series resistance. The voltage source equal to I naught R naught. This is the current source here, and this is the value of the resistance. If you know Vs and Rs, the voltage source and the series resistance, then the Norton current or the equivalent current source is Vs over Rs. Okay, it's very straightforward, and it's very helpful in some problems in simplifying the circuits. Okay, let's consider this example here. We have a circuit. This circuit has two sources, 5 ampere current source and 50 volt voltage source. These are both independent sources, and I would like to find the current flowing in the 10 ohm resistor. Okay, so of course you can do this in many ways right now. We can do nodal analysis, we can do loop analysis, we can do superposition, but I'm going to be doing it a little bit different way. I will try to convert this circuit into one loop. Okay, so what I'm going to be doing, I see here a current source in parallel with the resistor. So I'm going to convert these two into a voltage source of value 20 multiplying 5, so 100, in series with the resistance of 20 ohm. Okay, and I will try from that to get a more direct expression and convert this whole thing, if I can, into one loop, or one calculation will give me the current. Okay, so let's see how we can do that. So here I simply redrew the circuit, and I just mentioning what's my strategy here. I'm gonna convert this 5 ampere in series in parallel with a 20 ohm into one voltage source of value 5 multiplied by 20 in series with 20 ohm. Okay, and so this will open up this loop, and this will become part of the bigger loop. So let's see how this looks like after we make this simplification. Okay, so this is how the circuit now looks like. My target is to find this current I, the current flowing in the 10 ohm resistor. You can see that the voltage between this point here and the ground is equal to 100 volts. The voltage between here and the ground is 50 volts, okay? Then I can simply get the current flowing here. Notice the current flowing here it will be equal to 100 minus 50 divided by the total resistance. You have to take this 20 ohm into account, okay? So you see 20 plus 10 plus 20. Don't make this mistake and ignore this 20 ohm, because this 20 ohm also is in the loop. Okay, so I have here 100 volts between here and here. I have 50 volts between here and here. I have a total resistance of this loop of 10 plus 20 plus 20. Then this will be my current. 100 minus 50 divided by 20 ohm plus 10 ohm plus 20 ohm is equal to 1 ampere. So I was able just through one step to get the current. I did not have to do loop analysis, not have to do nodal analysis with multiple loops or multiple nodes or superposition. Just one source simplification opened up the problem, converted effectively into one loop. This other loop is a little bit redundant. Why is redundant? Because I know what's the current flowing in this 30 ohm. It's 50 divided by 30. Okay, so this is effectively here we have only one major loop that we can use to calculate the current I. Okay, let's consider this other example. We have here a second example. We have two sources, a 2 ampere source here, 2 milliampere current source, 12 volts voltage source, and we have a number of resistances. My target is to find V naught, and they asking me to use source transformation. So what I will try to do here, I will try to keep this 4 ohm. I'm not gonna remove it from the circuit, and I will try to reduce this whole circuit into one loop. Of course, getting V naught can be done in many ways again. You can do loop, second loop, third loop. You can have 3 loops, solve 3 equations, 3 unknowns if you want. You can have nodal analysis, so one node, second node, a third node, maybe take this one as ground. Okay, you can have it. You can do superposition. First use this source and then use this source, and then you sum the 2 V outputs, so you get here. So these are all possible techniques, and I encourage you to try this this example using these techniques. What I'm going to be using, I will use simplification using source transformation. So I will try to open this problem and convert this into one loop containing the 4 kilo ohm resistor. This is my target here. So I could see here I have 2 kilo ohm. This 2 kilo ohm is in parallel with the 2 milliampere. Don't get confused. This point is the same as this point. Okay, so these two in parallel with each other. So I'm gonna put here a voltage source of value 2 milliampere by 2 kilo ohm will give us 4 volts in series with 2 kilo ohm. Remember the polarity, this one is trying to push current this way, so the voltage source will also try to push current in the same direction, so polarity will be negative, positive. Okay, so remember the value of this voltage source, 2 milliampere multiplied 2 kilo ohm will be 4 volts, and it's going to be in series with R equal to 2 kilo ohm. So let's see how the circuit looks like after we make this step. So we got rid of the current source, and now we have this voltage source, this resistance here. This is how the circuit now looks like. Notice the polarity of the voltage source. It's trying to push current in the same direction as the current source. Okay, now we can do one more step of reduction. How? Let's see. I want to open up this loop, so this is how I'm going to be doing it. I'll do it in 2 steps. I have here a voltage source in series with the resistance, so I'm going to convert this one to a current source in parallel with the resistance, and this current source will be connected between this point and this point here. Okay, the value of the current source will be 12 volts over 6K will give me 2 milliampere, and it's going to be in parallel with 6 kilo ohm. Once I have done this, you will see that the circuit now will look something like this. There is a resistor here called 6 kilo ohm, okay, and it's going to be in parallel with a current source, and this voltage source is gone already. Okay, so this voltage source is gone, this resistance is gone, and now I'm going to combine this resistance because they are in parallel, and I'm going to convert this one back to another voltage source. Okay, so what I'm gonna be doing here, I will try to open up the circuit. I will remove all these steps I have done, and we'll see how things will look like. So this is my target. Replace this voltage source and this current source, this voltage source and this resistance by a current source in parallel with the resistance, and then I will combine this new resistance with the 3 kilo ohm to get one equivalent resistance, and then convert that current source again to a voltage source. By doing so, I will end up with only one loop in the circuit. Okay, so let's see how we're going to do that. So 12 in parallel with 6K, the current value is 12 divided by 6K is 2 milliampere, and it's parallel with 6K. Let's see this step. So this is now how the circuit looks like. I created this current source in parallel with this resistance. But the good thing is, if I combine 3K and 6K, they are in parallel. You can see they are connected in parallel. 3K by 6K over 3K plus 6K will give us 2 kilo ohm. So this source is in parallel with 2 kilo ohm. I'm gonna convert it back again to a voltage source in series with the resistance. So I'm gonna now do this now. I will replace this branch by a voltage source in series with the resistance, which is 2 kilo ohm. Why it's 2 kilo ohm? Because 2 kilo ohm is simply equal to 6 kilo ohm in parallel with 3 kilo ohm. What is the value of this voltage source? It's going to be 2 milliampere multiplying 2 kilo ohm, so it's going to be 4 volts. So this is now how the circuit looks like after I did this sequence of transformation. This is 4 volts. This is 2K. I still have my 8K there. I still have the 4K there. I have the source and its resistance. Now the circuit is one loop. I now can use current division, voltage division to get the voltage here. The total voltage in this loop is 4. I have 4 volts plus 4 volts. I have 8 volts. Then I want to get how much of this 8 volts appears across the 4K. I have here 4K, I have here 8K, I have here 2K, I have here 2K. Okay, so it's gonna be 4 divided all by 4 plus 8 plus 2 plus 2, so it's gonna 4 plus 12K. So this is gonna be 1/4 of the voltage will appear at the output, so this is gonna be equal to 2 volts. So this example is really a good example because it shows you that through a sequence of transformations, I can open up a circuit into one loop. In some cases, this is possible, of course, not in all cases. But I was able just to do through a sequence of source transformations to convert my circuit into one loop. Notice I did not touch the 4 kilo ohm because I'm looking for the voltage across the 4 kilo ohm. Okay? I got a voltage source. I converted a voltage source to a current source, and then a current source to a voltage source, and then I opened up with this wonderful loop here, just one loop. The solution is obtained in just one line and it's equal to 2 volts. Okay, so source transformation can be very useful in obtaining our solution. The second subject I would like to cover in this video is the concept of maximum power transfer. Very often we connect a load resistance to some source, and this source will have its own resistance called RS. Or this resistance is connected to a linear circuit. So someone may want to imagine that this whole thing here, okay, represents an equivalent circuit of another bigger circuit. So there is a linear circuit happening here, okay? I just call it LC. LC means linear circuit, okay? So a question that we want to answer right now: what should be the value of RL to get maximum power delivered from this linear circuit to my load? Okay, remember, every time you put RL here, there will be some power delivered to that load. Okay, how can we make this power maximum? This is a very important question we face in electrical engineering. If you design a certain component, you want to make sure that it is receiving the maximum power from the source. Okay, so this is called matching. You do matching, and this concept of matching is widely used even in AC circuits, and we'll talk about this later in the course. So let's see how we can analyze this circuit. We have an equivalent circuit. They have a voltage source. We have its own resistance in series RL. What is the power delivered to RL? The power delivered to any load, as we know from chapter 1, that it is the current flowing in this load multiplying the voltage across this load. The current flowing in this load is V over RS plus RL. So this is the current. Okay. The voltage across this load, we have a voltage divider. So V multiplying RL over RL plus RS. Okay, so this is what we have here. So this is the voltage across the load. This is the current through the load. If you multiply them, you get V squared RL over RL plus RS squared. As you can see, increasing RL, we have two terms. RL appears in numerator and denominator. So there is a specific value for RL that makes this quantity maximum. Okay, and let's see, if you make RL equal to 0, the answer will be 0. If you make RL equal to infinity, the denominator becomes dominant and you get 0. So there is a value in between that makes your power maximum. So let's try to derive this value, and it's the same way we learned from our calculus studies. You have to differentiate this expression relative to RL and set the derivative equal to 0. So first there is this one squared, this becomes RL plus RS to the power 4, and then the denominator multiplying by the derivative denominator, you get 1, we're differentiating relative to RL, minus the numerator, so minus RL multiplied by the derivative of the denominator, which is 2RL plus RS. And then we simplify this one and we set it equal to 0 to get the value of RL that gives us maximum power transfer. Okay, these are simply calculus steps here. I did the differentiation, squared the denominator by the derivative numerator, which is 1, minus the numerator by the derivative denominator, which is 2, multiplying the bracket. You collect all the similar terms, and you expand this one to RS squared plus 2RL RS plus RL squared. Set the numerator to be equal to 0. You will get that you see that you get two solutions. You get either RL is equal to minus RS, which is rejected because I cannot have negative resistance. So if RS is a source resistance, this is the one that's given, is equal to 50 ohm, I cannot have a resistance of the load is equal to minus 50 ohm. This is not physical. The second condition that you're going to be getting, of course, it's obvious. If you take RL plus RS out, you end up here RL plus RS minus 2RL. This is the second bracket that we have here. Okay, so this one equal to 0. If you do this one equal to 0, you obtain that RL must be equal to RS. And this is a condition that all electrical engineers know by heart. In order to maximize the power delivered to the load, then the load must be equal to an impedance equal to the impedance of the source. The value of the source or the load resistance, here we'll talk about resistances, later we'll talk about impedances. The value of the source resistance must be equal to the value of the load resistance. So you have to select your load so that it is matched to the source. Okay, very often maybe you hear about, you see, the coaxial cable entering your home is 50 ohm, so it must be connected to a circuit that has an input impedance of 50 ohm. This is called matching, and it's used very often. This is the final conclusion I would like you to remember. To get maximum power transfer from your source to your load, the load resistance must be equal to the source resistance. RL must be equal to RS. Okay, let's take a look at an example here. We'd like to find the maximum power transfer, maximum power that can be delivered to RL, and what is the value of RL that will give this maximum power. So this is a circuit. It's a big circuit. It has many components, can be even bigger than this. Because of this circuit here, it supplies certain power to RL. Our question is, what is this maximum power that can be delivered to RL? What is the value of RL that will give this maximum power? So what we can try to imagine, you can imagine that this is a controlled resistance. Okay, so we can change its value. Okay, and now we are playing with this value until we get maximum power transfer. Okay, so but we are not really doing it in a physical system. We are doing it using pencil and paper. So what you have to do, the way to do this is that we usually apply Thevenin theorem. You have to replace the circuit here. Looking into the circuit, you have to replace it by a Thevenin resistance and a Thevenin voltage source. So this is V Thevenin, and the other one is R Thevenin. Okay. Okay, and then you have your resistance RL connected to these two. And from our previous discussion, RL must be selected to have the same value as R Thevenin in order to get maximum power transfer. What is this maximum power transfer? I can calculate it from this equivalent circuit. So now you could see that the problem now will be converted to finding the Thevenin equivalent looking into my circuit. So I have to find the open circuit voltage, which will be equal to my Thevenin voltage, I have to remove all the sources, all the independent sources, and then trying to find the input resistance. This will give me the Thevenin resistance. Once I have done that, I know that I get maximum power transfer if RL is equal to R Thevenin. Okay, so let's see how we can proceed in doing that. So the first step in solving a problem like this one, I have first to find the Thevenin equivalent looking into the circuit. So I have to create an open circuit between these two terminals or at this port. Okay, so this slide summarizes what I said. You have a load connected to a certain linear circuit. And what we're going to be doing, we're going to replace this whole linear circuit by a Thevenin equivalent. And we know from our maximum power transfer condition that you get maximum power transfer to the load if RL is equal to R Thevenin. And this power can be calculated because if this one is equal to this one, then 1/2 of the Thevenin voltage will appear across RL. I can calculate the power. I will have no problem in calculating the power. Okay, so let's first get the Thevenin equivalent. I will create an open circuit between here and here, and I'll try to calculate the open circuit voltage. So this what I did, I created an open circuit, and now I want to calculate this voltage. This circuit is very special because you can see these are actually two circuits, two separate circuits, and they only meet at one point. So there is no return of the current of this 2 milliampere to this circuit here. So this 2 milliampere will only flow here, and this loop will be on its own as well. Okay, so these are actually two independent circuits. You're just meeting at one point, and what we have to do, we have to say that the V open circuit is equal to this voltage drop plus this voltage drop. This voltage drop here is equal to 2 milliampere multiplying 2K. This voltage drop here is obtained from a voltage divider. It is 6 multiplying 6K over 6K plus 3K. So we have here, this is the expression for the Thevenin voltage, which is the open circuit voltage. It is this drop plus this drop. Remember, these two are, this source cannot supply current to this circuit, okay, this other circuit, and this source cannot supply current to the other circuit. These are two independent circuits because they meet only in one piece of wire. There is no return current from one to the other. Okay, the drop here is equal to 2 milliampere multiplying 2K with this polarity. The drop here with this polarity, positive, negative, is 6 volts multiplying 6K over 6K plus 3K. So this one here will give me 6 over 9. So this will give me 4. This one here will give me 4 volts. Then the Thevenin voltage is equal to 8 volts. Okay, so now we calculate the Thevenin voltage. Second step is find the input resistance seen into this one. And as we did before, you have to remove all the independent sources, make a voltage source short circuit, make a current source open circuit, and then see the input resistance looking into this side. This circuit does not have any dependent sources, so I can calculate the resistance directly. I don't have to connect an external source and then calculate the external current. I don't have any dependent sources here. So I will make this one open circuit, I will make this one short circuit, and then I'll try to find the input resistance. And let's see how the circuit looks like after we do that. So similar to the steps we did before, I removed all my independent sources, the voltage source short circuited, the current source open circuit. I'd like to calculate the input resistance. This input resistance will be equal to R Thevenin as we explained in a previous lecture. So this resistance here is 2 kilo ohm in series with this parallel combination. 6K multiply 3K over 6K plus 3K will give us 2K. So this is effectively 2K in series with 2K. So the input resistance is effectively 4K. So this is how the circuit now looks like. We have a load, it's connected to a Thevenin voltage of 8 volts. It's connected to a Thevenin resistance of 4 kilo ohm. To get maximum power transfer from this 8 volts to the load, RL must be equal to 4 kilo ohm as well. The load resistance must be equal to the source resistance, which in this case is the Thevenin resistance. Okay, so we know what is this value. RL, the value of RL that gives us maximum power transfer is RL equal to 4K. What is this power? What is this power? If these two are equal and each one of them is 4K, then the voltage across this one will be half the source. So this is 4 volts. Then the power will be 4 volts squared divided by RL. Okay, so 4 squared divided by 4K will give us 4 milliwatts. Or you can find the current. The current will be 8 volts divided by 8K will give me 1 milliampere. So it's going to be 1 milliampere multiplying 4K will give you also 4 milliwatts. Okay, so the power delivered here, you can do it in many ways. VI or I squared R or V squared over R. This is 4K, this is 4K, this is 8 volts. I know everything about the circuit, so I know what is the power delivery. So the maximum power you can deliver is 4 milliwatts. I would like you to go and repeat, consider this circuit again, but select other values for RL other than 4K. Select it as 8K or 10K, and each time calculate the power delivered to this load here. You will see that your power will always be less than this number, 4 milliwatts. So 4 milliwatts is the maximum power that can be delivered from your source.